Hello everyone, welcome to EPG Pathshala. I am Dr. Roshan Livingston, working as a medical physicist in the Department of Radiology, Christian Medical College, Vellore. The module which I am going to cover today is on digital imaging. This module comes under the topic radiation biophysics. Why do we need to know about digital imaging? High quality healthcare is important in this current scenario in our country, and it is through digital radiography. The older systems had film screen radiography, but the newer ones, which are digital radiography, deals with filmless technology, which can be sent to PACS, that is Picture Archival Communication System, which doesn't need a film. And there are a lot of options available which can be used by the clinician to diagnose good clinical indications as well as diseases. The various types of detectors that are used for routine radiography as well as mammography includes computed radiography, indirect flat panel detectors, as well as direct flat panel detectors that can be used for mammography purpose. Let's consider looking into this computed radiography cassette. This cassette has its detector inside. The detector is made out of photostimulable phosphor plate. These phosphors, once they are hit by X-rays, they form a latent image. The latent image is an invisible image. When struck by a source of light, which is like photostimulable, it will produce energy level in the form of light. That light we need to take and convert them into electrons as photoelectrons and form an image. This illustrates the function of a computed radiography system, which is seen in a hospital scenario. Here you can see an X-ray tube and a patient and the cassette. The following image, what you see here, is a CR reader. What happens inside the CR reader is this latent image, which is the invisible image, is converted into a visible image and seen on an image as a chest X-ray visualized in this illustration. The main components of a computed radiography system is the image phosphor plate, the laser light which is going to be used to stimulate the invisible image, and that image to be visualized as a digital image, we use a photomultiplier tube. Coming to components of the CR system, the image phosphor plate. As seen in this image phosphor plate is taken out of the cassette. This is the image phosphor plate, which contains barium fluorohalides. Specifically, most of the companies manufacture this material with barium fluorobromide doped with europium 2+. And this is the front side of the IP plate, where X-rays come and impinge on this plate and then forms a invisible or latent image. This IP plate containing barium fluorobromide has also impurities, which are nothing but dopants. These dopants are europium 2+. When X-rays interact with this material, it raises the europium 2+ to europium 3+. This europium 3+ is nothing but a trapped electron center. So hence, when X-rays fall on this plate, there are numerous trapment centers which has europium 3+. It is said that about 25% of loss can happen in the IP plate if it's not read within 10 minutes to 8 hours. This phenomena is called fading. This IP plate, which is now containing the invisible latent image, is now fed into a CR reader. Inside the CR reader is helium neon laser, which gives red light of the spectrum. This photograph shows the internal components of a CR reader, and it also shows a laser assembly as well as optic coupling. The following diagram illustrates what is happening inside the CR reader. The CR reader has a laser source and it has a beam splitter. Well, one part of the beam goes to the reference detector and to the beam deflector. From the beam deflector, the beam is deflected to the F theta lens and to the cylindrical mirror. From the cylindrical mirror, it is channeled through a light channeling guide, and this is absorbed by a photomultiplier tube, and from the photomultiplier tube it goes to the amplifier and to the analog to digital converter for the processing. When the IP plate goes inside the CR reader, the light from the laser passes through a beam splitter. The beam splitter checks intensity fluctuation using reference detectors. The F theta lens gives a constant focus and linear sweeping velocity across the photostimulable phosphor plate. And there is this mirror which scans each line of the IP plate. When the laser source falls onto this IP plate, the europium 3+, which were activated because of this X-ray image formation, falls down into europium 2+ by releasing an energy of about 3 electron volts, which is nothing but a light photon. The photostimulable light that is formed because of the laser is channeled into a photomultiplier tube through this optical coupling, what you see here. The photomultiplier tube converts light into photoelectrons. These photoelectrons are accelerated and amplified through a series of diodes within the photomultiplier tube. The data from the photomultiplier tube is digitized using an analog to digital converter, and this stores in a digital image matrix. However, there is some kind of latent image still present into the IP plate. Now, how do I remove that latent image? This is by focusing with a highly focused sodium vapor lamp or a halogen lamp, so that this high intense light will erase the entire CR IP plate, and it is ready for use for the next X-ray imaging. Let's summarize what is present in this computed radiography system. The IP plate, which has the barium fluorobromide, when X-rays are exposed to this IP plate, they create a latent image. When a laser beam is scanned on that, the latent image gives the image formation. And finally, little bit of latent image is still present, which has to be erased by intense light. And however, this entire IP plate can be reused after erasing, so that the waste latent image is removed from the plate. The advantages of the CR image phosphor plate or the CR cassette is that the existing X-ray machines can be used. You can replace the film screen combination with this kind of CR cassettes. They can be used for mobile radiography machine, and if a single image plate is having artifacts or it has artifacts, it can be removed and replaced with a different IP plate, a newer one. Radiation dose to the patient is reduced if optimized exposure factors are included in the radiographic techniques. Next, we move on to digital radiography systems. In a digital radiography system, there are flat panel detectors which has indirect conversion. In the indirect conversion, we have charged coupled device and amorphous silicon technology. In the direct conversion, we have amorphous selenium technology. Let's talk about indirect conversion technology. And we talk about charged coupled device, CCD. The general principle is X-ray photons, which are produced from an X-ray machine, and a scintillation material. The use of scintillation material is when X-rays fall on the scintillation material, it produces light. Cesium iodide or gadolinium oxysulfide are used as scintillation materials. And then we take it through the optics. In some cases, we reduce the size of the image. And finally, the end product, which is the image, falls onto a charged coupled device camera, which converts the light into an electrical image. Let's consider the Ccd technology. And if I consider a patient who is coming for an X-ray, chest X-ray, and then it has a 1417 screen, the scintillating material is completely embedded on this 1417 area, and when X-rays fall through the patient, the transmitted X-rays falls onto the scintillation material. The scintillation material converts X-rays into light photons, but it's now in the form of an X-ray image and a light image. This light image is channeled through optic tapers, or in some cases fiber optics, and then falls onto a very small area which can be 1 centimeter square or 4 to 5 centimeter square, a CCD camera, which are nowadays used in cell phones. In another type of CCD technology, it can have a lens coupled CCD, where lenses are needed to reduce the area of the projected light to fit into one or an array of CCDs. As you are seeing into the image, X-rays fall onto the scintillation material, which can be 17-14 inches. The scintillation material produces light, and the light is channeled through optic lens, and there is one single CCD, or also can be an array of CCD, to absorb these light photons and convert them into an electronic signal to produce an image suitable for medical imaging. Another technology for using CCD is a slot scan CCD. In this kind of technology, a collimated fan shaped X-ray beam is linked to a simultaneously moving CCD detector, and the readout process is similar to what we have just seen before. The advantages of a CCD based system is that it is not too expensive. However, the disadvantages is it has an optical coupling, and then image may be demagnified to fall onto one CCD camera or an array of CCD camera, where it may lose some of the image information. These are usually used for chest radiography, for dental imaging, orthopantomography, or in mammography systems these days. The second part of the indirect conversion flat panel detector is the amorphous silicon based technology. The general principle of this amorphous silicon technology is that when X-rays fall on to the patient and the transmitted X-rays fall to a scintillation material. Here too we see it may be a 17-14 inches area which has the scintillation crystals. The scintillation crystals are made out of cesium iodide or gadolinium oxysulfide, as seen in the CCD based system. Instead of the optic coupling there, we use amorphous silicon photodiode array. The function of this photodiode array is to convert light into electrical signal, followed by which there is thin film transistor, also called the TFT, which is a readout array, and it acts as a switch. In this amorphous silicon technology, amorphous silicon and various metals and insulators are deposited on a glass substrate to form a photodiode array and a TFT matrix, as shown in this figure. In this figure, we see a scintillation material which is here shown as cesium iodide on a glass substrate is shown as a sandwich. In this amorphous silicon technology, as we know that when X-rays fall onto the scintillator material, it converts X-rays to light. The work of this amorphous photodiode array is to convert light to electrons, and it actually forms a bucket of electrons for each pixel. The function of the TFT, as it acts as an electronic switch, it collects the charge from the photodiode at every pixel, and it reads out into the electronic system, and this can be directly displayed onto a monitor. The advantages of an amorphous silicon technology is that it can be used for bedside radiography. Nowadays we get cassettes which have this kind of flat panel detectors which are based on amorphous silicon. In some cases we use amorphous silicon with cesium iodide scintillator material, which has more spatial resolution compared to the gadolinium oxysulfide. Hence, gadolinium oxysulfide based detectors are used for bedside radiography. So, the existing X-ray machines where we have the bucket tray, this kind of retrofit DR system based on amorphous silicon can be fixed in order to receive this image formed due to X-rays, and this can be directly viewed onto a monitor. Next, we move on to a direct flat panel technology which do not have a scintillator material in it. Let's see what is there in this technology. The general principle of direct flat panel technology is X-ray photons. As usual, there's an X-ray machine. Instead of amorphous silicon, we have amorphous selenium here. The amorphous selenium is a photoconductor material which directly converts X-rays into electrical signal, followed by a thin film transistor which is a readout array which acts as a switch, similar to what we saw in an amorphous silicon technology. Now in this direct flat panel technology, which is based on amorphous selenium, a bias voltage is applied across the detector which contains this amorphous selenium material. In this amorphous selenium technology, incident X-rays are absorbed by the detector directly and generate electron hole pairs. The selenium detector layer is overlaid onto an array of thin film transistors which collects the electronic signal and amplifies them to form a radiographic image, as seen in this image. This amorphous selenium technology is not indirect because there is no light conversion, and hence it is a direct electron hole pair creation because X-rays fall directly on the detector material. Hence it has high spatial resolution. That means the ability to see two different objects separately. Though the cost is very high and it has superior spatial resolution compared to the indirect method of acquiring images, this kind of technology is used in mammography purpose. Let's recap of what we have discussed right from the beginning in digital imaging. In digital imaging, it is possible to acquire images digitally either using a computed radiographic cassette or flat panel detectors. The advantages of this digital imaging is that it has several options available so that enhanced medical care can take place by using various algorithms. This makes it more user friendly and it can be transferred to many places compared to the film screen radiography, which has only one image. Of course, when you use this kind of digital imaging, this can be routed through the picture archival communication system through various hospitals or using a telemedicine. The computed radiography system uses an image phosphor plate which has barium fluorobromide doped with europium-2+. And when X-rays fall on that, this europium-2+ becomes europium-3+. When this cassette is fed into the reader, the laser present inside the CR reader stimulates the europium-3+ to form europium-2+. By the way, it gives a small light photons which is useful for imaging purpose. This light photon is absorbed by a photomultiplier tube for image formation. In an indirect method, CCD cameras are used as well as amorphous silicon is used. In both this technology, scintillation material, either cesium iodide or gadolinium oxysulfide, are used as scintillation material. The work of the scintillation material is to convert X-rays to light. Now we need to convert the light into electrons. We use optic tapers, and on a CCD camera it falls, or we also have amorphous silicon photodiode array and a TFT, which will convert the light into an image formation so that it can be viewed on monitors. In a direct flat panel system which has amorphous selenium technology, X-rays are directly converted into electrons to form an electronic image which can be used for diagnosis. I hope you understood the basic concepts of digital imaging in this module of digital imaging. Thank you very much for your attention.